I'm gonna give a quick introduction to our speaker here. So today, please welcome me in joining Dr. Alexis Achim. He's a professor of forestry and wood science at Laval University, as well as the director of the Renewable Materials Research Center. Alexis Achim obtained his bachelor's degree in forest management from Laval University in 1998. After obtaining his PhD from the same institution in 2004, he joined forest research in Edinburgh, UK, where he specialized in wind throw risk evaluation and wood quality modeling. He came back to Laval University as an assistant professor in 2007, and since then has developed a research program at the nexus between forest management and wood science. Part of his current research aims to use airborne laser scanning to assess structural attributes of forests and link them to stand dynamics, tree growth, and wood properties. This has led to the development of the Lidar package in R, which has been widely adopted by the scientific community. Again, please welcome me in joining, or please join me in welcoming Dr. Achim. Take it away.
Thank you, John. Well done. You did a good job pronouncing my name in French. I appreciate this. Thank you, everyone, also for being there. It's a real pleasure to be connected with you today. As I said to John before, and I could not really say no to this invitation because I've asked David Auty to do exactly the same for me. He was speaking from Arizona to my Laval students in this case. I see there's a lot of faculty also connected to the presentation. I'm really happy that you're taking the time to listen to what I'm going to say. So what I'm planning to do, I'll share my screen. Will attempt to summarize the work we've done on LiDAR, and in doing so, try to make the case for packaging your work. And I will describe how we've done it, what were the benefits for us. And I hope I will be able to convince people that it's a good idea to apply the same principle, maybe not in the same way, but it's a good idea to apply the same principle in your research. So I think the idea is to have a thought-provoking discussion or presentation so that we can have the discussion afterwards. So I assume everyone can see my presentation all right. I will keep going. So just as background, I work for the Renewable Materials Research Center at Laval University. It's located in Quebec City, east of Canada. And we have about 14 professors working on what's joining us together is we work on wood as a renewable material. So it's basically the wood science, the equivalent of a wood science department. And for me, who's nearer to the forestry practices, I've been working on LiDAR mainly as a way to characterize future wood supplies. But of course, I understand that there's a lot more interesting topics that we can study with using this technology. And so my presentation will not be focused on wood. So the overview of my presentation, my objectives for this presentation is first to give you a short introduction of what LiDAR is. I think a lot of people among you will know what it is. Then I'll give an overview of the LiDAR package. And most importantly, my third and most important objective for this presentation is that at the end of the presentation, I'll try to make the case for the principle of packaging your work. And I'll explain what I mean by that. But if we start, in terms of LiDAR, of course, LiDAR is the sensor and the technology itself, but it can be embarked on anything, whether it's an iPhone or a car or whatever. But here I'm talking about aerial laser scanning, talking about LiDAR technology embarked on a plane that will then sample the forest and provide wall-to-wall assessment of forest structure. And of course, we have we represent LiDAR in this way, aerial LiDAR scanning in this way, as this kind of beam that goes through the forest. But in reality, what we have, I've just dropped my, yes, okay, now I can see the whole presentation. So in reality, what we have is a series of impulses. So those beams that will be sent towards the forest, and they will come with knowing the speed of light in the speed of travel for light. We will be able to know when the beam has hit an object, and for the time it returns, we can estimate the distance between that object and the plane. And so what we've been working on is this process, and trying to make sure that we can analyze this data in the best way as possible. So there are two main approaches that are used for analyzing LiDAR data. The first one is called the area-based approach, which basically consists of linking ground plots, often 400 meter square ground plots, to the structure of the point cloud over that very same ground plot. So it's very important that those ground plots are well positioned geographically. And then models are developed between some metrics that are extracted from the 3D structure of the point cloud and some variables of interest in the ground plot, such as it could be, well, the easy ones would be tree height, but you can have the volume of the plot or the basal area of the plot, and then you develop a model for your plots, and then you can apply the predictions wall to wall over a forest, usually using the same size pixels. So in this case, they would be each of the pixels on this image would represent a metric that we have predicted on 20 by 20 meter pixels. The other approach, which is easier to apply in forests such as ponderosa pine forests in northern Arizona, they are a little bit more open. So then we can start using the same type of data to delineate the trees. But of course, to delineate those trees, you need algorithms to do that. But once you apply those algorithms, you can delineate the trees, and then each tree within the forest becomes an object, and then you can extract any type of metric about the size, the height, the crown size of this tree at an individual tree scale, which is quite interesting. In practice, for broad scale inventories, we've been working, this is the province of Quebec in Canada. It's a very large province. It's the largest in Canada in terms of area. And the Ministry of Forests, Wildlife and Parks in Quebec has made the decision about 10 years ago to fly over the entire productive forest estate. So that the northern limit of forest management would be about here in Quebec. And so all this zone has now been covered with aerial LiDAR scanning acquisitions. So that was a huge program. It took about 10 years to acquire, and now we're going to enter the second phase of that acquisition. They have decided to go for a second phase, for a second acquisition, to try to use consecutive LiDAR acquisitions to try and monitor the evolution of the structure of the forest over time. So the reality that we were working in was that we had to work with data that was acquired by several providers using different devices, different settings, and different times of use. So there was important variation in the sampling. And that meant that we needed to work on some of the issues. Our partners wanted us to work on some of the issues that were related to the differences that they were seeing between contracts, often even in the same region. So when we're talking about these differences, what were they? Aside from the equipment, we have, if we take this as the reference, we have the density of the point cloud that can vary. It can vary locally. It could vary between acquisitions as well. we have the intensity of the beams that are being sent by the Lidar sensor. And so that also will have an effect on the readings. There can be differences in footprint. So the width of the beam that's being sent will also influence the structure of the point cloud. The pulse duration is another thing that will influence the structure of the point cloud. The maximum scan angle is another thing. And then there's also the aircraft elevation. So the higher up the aircraft, usually the less intensity we have. And of course, we can have lower density as well. It depends. Anyway, so you can imagine it's cheaper to fly higher, but it will produce different results. And finally, there's also the electronic system of discretization. So basically, we are seeing, when we look at LiDAR data, we look at a 3D point cloud. However, before we get to a point cloud, what actually the sensor was able to get was the full waveform of the returning beam. And so then there needs to be an algorithm that's it's always proprietary. This algorithm will need to decide where are the objects that were hit in this full waveform. So one algorithm could decide, okay, there was one object here, one other one here, and another one there. So there were 3 objects, would have 3 returns. But another one could have a lot more than that. And there could be an argument that there are only 2 objects that were hit. And so this design in the sampling is what we tried to tackle. So I've sent along with my presentation 3 papers. The first one described the work that we've done on how to take into account the variation in density in trying to assess a simple metric that is often used in LiDAR studies, which is the height of the canopy. So, what I'm describing is it could be seen as something trivial, but it's actually a real problem. So here, what we had is 2 acquisitions taken at the same place, where we had a low to medium density acquisition, the typical one that you would see at about 3 or 4 points per square meters, and a high density acquisition at about 20 or 30 points per square meters. And if what you can see on this graph is that there is 1 meter bias in the assessment of the height of the canopy between the 2 acquisitions. And this is because they were acquired with these different settings, and density is an important part of that. The principle is quite simple. So it's all a game of probabilities. So if you have very few pulses, like I'm representing here, you have little chance to actually hit the highest point of the canopy, right? And if you have more pulses, then you have more chance to measure something that's close to the top of the canopy that's here. And if, again, you have more pulses and you have a higher density, then there's a high chance to be measuring something that's very close to the actual maximum height of the canopy. And one thing also that we noticed, well, we in our conceptualization of the problem, we also understood that there was a structure dependency. That means that the structure of the forest will also have an impact on the bias that you will see. So basically a hardwood forest here that has a more even canopy, even with few pulses, you are quite likely to be quite close to the top of the canopy when you sample with very few pulses. So there's this structure dependency that we needed to think about. Knowing that this problem was relatively simple, we understood that there was an analytical solution to that problem. So there's a lot of illustrations in the paper I gave along with the first paper I gave along with the presentation, but it's actually very simple. In short, the analogy we can make is having a number of loaded dice with a number of faces, and then you want to calculate what the expected value of the highest score. And this depends both on the density and the structure of the forest. So here, the number of faces is the accuracy of the model. The loading would be the complexity of the canopy, the structure of the canopy, and the number of dice would be the number of points that we would have. And applying this analytical solution, what we were able to do was to, well, first correct the bias, but it's more than correcting the bias because it's not a global shift that we applied, but every pixel, 20 meter by 20 meter pixel, was corrected. So all shifts were independent. And it's not only the bias that was removed, but also the level of correlation between the two samplings or the two acquisitions was made higher. So we demonstrated a causal relationship relying on the random nature of the point distribution. So this was all cool. And this was published and it was well received. But when we analyzed the data, we found that there were other sources of bias including the effect of scan angle. So we could see that there were biases according to the scan angle. So here, when we are at the extremes of the sampling, we were able to see that there were differences between the two acquisitions that were just related to what was the difference in scan angle between one acquisition and the other. So we knew we needed to work on scan angle. So that's what the second paper that I gave along with the presentation, that's what it tackles. And again, there's a lot of complicated, well, it's not that complicated, but there's a lot of maths in this paper, but I think I can summarize it quite easily. You know, from what we were trying to do is to say, is there a way that we can remove this effect of scan angle in the data? And so what we wanted to simulate was a plane that would sample only directly below. That's what I can never pronounce this word in English, but I think it's nadir or something like that. So anyway, vertically. So can we simulate a vertical acquisition? And there are two different theories or two different ways to approach this problem. In conifers, we would normally use optical geometrics, which is basically shadowing. But in northern hardwood stands, we can use more radiative effects, which were a little bit simpler to deal with in the case of our problem. Also, it corresponded with the forest that we were sampling. So basically what we can do is that we can consider the forest canopy as a turbid medium. And what happens when you send a beam through a turbid medium is that the longer the path across the canopy, the greater the probability it will get intercepted by one of its components. You know, so if I illustrate that, here we go. So we have the forest canopy that we represent with different densities, you know, a low density at the top, high density in the middle, and a lower density at the bottom. This could be any structure. This is just to illustrate the point. So if we sample vertically, then we would have points, you know, we have a proportion of the points that will be intercepted by the canopy. And if we go down, then we will get a proportion of the points, but it's the proportion of the points that have not been intercepted above, right? And so there's it's almost like Squid Game. There's fewer and fewer points as we go down down into the canopy. And of course, this is what happens when it's done vertically. But if you go at an angle, then the path is longer. So you would have a tendency to have more points towards the top. And when you're trying to derive statistics from the distribution of the points, if the scan angle is higher, then you would have a different view of the structure of the canopy. But it's not the structure of the canopy that has changed. It's actually the scan angle and the path, the length of the path that is required to be crossed. So again, we used similar principles, and we were able to model this behavior using probabilities again, and the model matched observations. And I'm not getting into the details here, but it can predict behavior and to different types of forests that had not been observed necessarily. So this would be, a canopy where most of the leaves are completely at the bottom, which doesn't really exist, but we can predict the behavior of what the metrics would be, how the metrics would be affected by scan angle. And this would represent a canopy that's top loaded, where most of the leaves are at the top, and you can predict different behaviors. So if you can see, like, for example, I think the yellow one is interesting here. You can see that with scan angle, this metric would tend to decrease with scan angle in bottom heavy canopy, but it would tend to increase with scan angle with a top heavy canopy. So again, that was all cool because we had some analytical solutions for our problems. Excuse me. So here we are. So all of this we were able to do. We were able to, well, what we're saying is that we were able to correct the scan angle effect and the density effect. Thus, we considered that we created like something similar to a standard device that could help analyze multiple acquisitions and compare them. This was all done, and this is my point here. I don't want to get too much into the detail. This was all a lot of fun. But to be able to do all this, we needed tools, we needed routines, we needed to have programs, computer code to be able to do that. And the most important part of my story is that this could have stayed in the computer of my PhD student at the time, Jean-Romain Roussel. I forgot to name him at the beginning of the talk. He did all the work, by the way. So I'm presenting this, but he did all the work. And it could have stayed in his computer, but it didn't. And that's part of the story. So that brings me to the case for packaging your work. This is what I want to transition, because the story is that he had an analysis to run. He had a lot of code to develop. And instead of just keeping the code on his computer, he decided to share it. And it went a lot further than we first imagined it would go. And so that I want to use this as an example to make the case for packaging your work. And I'll explain what I mean by that. Before I get into that, I want to make it clear that publishing is what we do, right? It's our, you can take it as our currency. In the same way as builders build houses, researchers publish their work. And I don't want this message to come across as diminishing the importance of publishing. That's not the point at all. So as researchers, I want to make it clear that our job, and the grad students listening, and I'm sure that faculty members agree with me, that our first job is to publish our results in peer-reviewed scientific journals. It ensures that our work is scientifically sound, or ensures, or as much as we can anyway, that the work is scientifically sound, and that it remains available over time. So those are two important advantages of publishing in peer-reviewed journals. And to be honest, also I think the reality is that the number of publications and their impact are certainly the main metrics that are being evaluated for any academic position. So it's important that the message that does not come across as the fact that we need to do something else than publish. That's not what I'm saying. What I'm trying to say is, rather than that, when we have done this, at this stage, the routines and programming tools that we have developed, they are useful to the first author, and only the first author, right? And so the idea is, what's next? What should we do next? And that's what I mean by packaging your work, is making it available to others so that it can be used. So let's discuss a little bit what's next. And I want to stress like 4 essential stages to making your programming tools useful for you, for your team, for your community, and perhaps beyond your community. Those 4 stages are publication, documentation, workable state, and sharing, right? So let's take all of them one by one. So publication. We need papers in which we have sound description of methods, either in the materials and methods when we have a scientific problem and we've developed a routine that could be useful to others. We want the paper to be fully reproducible, so we need methods to be described as much as possible, and ideally with code that comes with that. Otherwise, there can be also a paper that's fully dedicated to the method you've developed. So that's another step. And this is a very important step. But once this is done, if we put it bluntly, the world knows you have a script on your computer. The world cannot still use your script unless you've shared the code, and even then, it's difficult for a user to use raw code and apply it to their problems, right? So that's where we need to go a little bit beyond publication if we want to package our work and make it available to others in the form of the method that's been coded. So the documentation is the next stage. So it's important for any tool like this to be documented. Does it do? How does it do it? What are the inputs, the meaning of the inputs, the format, the range, etc. What are the outputs, of course? What is the content, but also what is the format of the output? How to install it? That's very important. Now, if we have sufficient documentation, then these tools may be useful to you and potentially to your lab mates. You know, I think it's key in research programs that these routines that are being developed, if you give them to your supervisor, the supervisor will first be extremely busy, unlikely to be able to use that routine himself or herself. And very likely this will, the supervisor will be able to pass it on maybe to some other student, some other user. And if the original student has disappeared or moved on or gone to some other greener pastures, there's a high chance that this tool will not be used. If there is proper documentation, there's a much better chance that it will be passed on. In terms of workable state, that's another step. And that's a step that starts when you start to share your work with others. And because when you actually use your code yourself, you know what not to do. You use your code in a way that you would expect. If you start sharing it with others, then people will use your code in ways that you cannot expect. And this will create errors for sure. So you need to run tests, you need to fix bugs, you need to search limit cases. And you need also to make it easy to install on all platforms. So those are key points that Jean-Romain and I, and mainly the work of Jean-Romain, the developer of the Lidar package, has been able to put together and learned sometimes the hard way. Once you're in a workable state, your tool cannot be shared more widely. And more sharing means more work on that workable state. The last step is to share your code on a public platform that's available ideally publicly and at all times, right? So there is a list that JR and I consider as in order of relevance. We think GitHub for sharing code because of the wide user community, but also all the tools it provides and also the version control. We think that's probably the ideal way to share codes and routines. Then we could go down, of course, GitLab is similar, SourceForge, and then you get to the supplementary materials of papers. So then again, if it's raw code that we're using, it's more difficult to use. It can be stored on a university server or any sort of cloud service that's available to, it could be a cloud service that's available to a team. But there is, even ideally you would share on tools like GitHub, on platforms, I should say, like GitHub, but at least if the developer in a lab has shared the code in Dropbox or OneDrive or Google Drive, at least it's becoming available to others. So the idea, I think, for students is to consider, okay, what code am I developing, and could it not be useful to others, especially the people that will follow me in the lab? And I guess that through developing the LiDAR package, what we've learned is that it's very difficult to anticipate who will be, or I should put it this other way. It's very easy to underestimate the usefulness of your code, of your routine, because usually we develop code for doing stuff that is both difficult and boring. And so if we have a way to make our lives easier, then people are likely to have it. And I think we were surprised to see how many people had the same needs as us in terms of analyzing, in this case, LiDAR data. So once these 4 stages are done, your tool can now be shared more widely and to different communities. So if we go more specifically to the LiDAR package for R that we've developed, this is a short history of the genesis of the LiDAR package. So JR, that's his short name, started his PhD just at the end of 2014. It was completely new to him. LiDAR was completely new to him. He he was part of the values of the lab, but also his own values were that it's all shared by several of you, I'm sure, but we wanted to have transparent workflows. So we wanted to have code that, or methods that would be reproducible, sorry. And so he started to code his own tools to analyze LiDAR data because he did not want to use proprietary software that was becoming, in scientific papers, that was becoming basically a black box. So he started to code a little bit. And after roughly a year, he had the first draft of the LiDAR package that he put on GitHub. And to be very honest, he put that on GitHub simply for his own needs for version control. We did not know really that there would be potential users for that. But very soon after that, here, you can see that LiDAR, the package already had several users, including some from Northern Arizona. So Andrew Sanchez Medor was among the first users of the package, and a very enthusiastic one. So that motivated us a little bit more to release it on CRAN in 2017. We then started to notice more and more interest, and we invested more into the development. So we hired an intern in 2018, and it's become a much more widely adopted package. But, it all started from a student that decided to share his code. And that's the main message there. And so this is the early developments. I'll give more details about the later developments later in the presentation. But for now, let's go back to those 4 stages. So we have the publication stage. We did it in reverse. We did it. It's only come out recently. 2 authors from Northern Arizona on this paper, but we've described the LiDAR package as a package. And in short, if we want to put the philosophy behind the development of the package is, as I was saying, we want to allow open source fully reproducible workflow. So we want to give that to the community. But also, we realize that in research, there is a need to apply, to test things, to do things that we would not necessarily have as a predetermined routine, right? So if I want to extract metrics from a LiDAR point cloud, and I can have a list of 100 metrics that are generic, but let's say that I imagine another type of metric that I want to calculate. I want to be able to calculate that metric. So we want to give that flexibility to users. Now, what I'll do is I'll just show you, because this will give you a nice start for me talking. I will just show you something. I will share my screen again. Sorry, I want to show you a video. Right, so this is what the package does. Right, here we go. So normally, tell me if you cannot see this video. Hopefully you can see it.
We can't see it right now.
Okay, great.
No,
You said you can?
We cannot see it, excuse me.
Cannot, oh, sorry. Okay, go back. What did I do?
There we go. We're seeing
Oh,
it
you've
now.
got it now?
Yeah.
Okay, so let's go back here. Okay, so that's what it does. So it's only a 2-minute video that shows what it does. So you can use LiDAR data and compute the digital terrain model. And then so you separate the soil from the vegetation. You subtract it, and that means you can put the vegetation on a plane. And then you get a normalized point cloud. Then you can do individual tree segmentation. So there are algorithms from the literature, several algorithms that were included in the package, embedded in the package. You could develop your own, but we've embedded those that we could implement from the literature to first identify treetops, and then segment the trees, and then extract metrics from individual trees. So you see that all the individual trees there. Quite importantly, it's coded in R. R is slow. So behind that, there is C++ programming. And also, you'll see there is a possibility to analyze, there's this engine for processing a set of tiles covering large areas. So what you do is you cover large areas, and there's a buffer around each tile to guarantee that you will have strict wall-to-wall output. So this will take a little bit of time. So this, for R, I think that's part of the success of the package is for R, the analysis is rather quick. It's not blazing fast like it could be with other programs, but the advantage of using R is we have a strong user community, right? Okay, so let me stop the sharing. I'll come back to my first screen. So are we back, John, with?
Yes, we're good to go.
Sorry, I had another video starting. All right, so okay, so I'm coming back here. So this is the package in short. The third paper I gave with the presentation is actually describes the whole philosophy and gives a lot of details around the package. Okay, so the publication is done. The documentation, we have a user manual. We have user-friendly tutorials that have been developed often by users themselves, not really by us all the time. We have worked on a Lidar book, which is complementary to the user manual that's embedded in R. The Lidar book can be found at this address. This is an image of the Lidar book. It contains a lot of pages and user-friendly tutorials, both for new and advanced users. And there's also a Lidar tag on Stack Exchange that hosts a lot of questions, and JR often, and other people often answer those questions on this tag. in terms of workable state, a lot of work has been done on making sure that it remains available on all platforms. Bug fixing is not so much, doesn't take that much time anymore, but it's still part of maintaining the package. One real challenge is that the CRAN checks are absolutely rootless. So CRAN is the comprehensive R archive network, and the big advantage of being there is that it becomes then very easy for any user to install the package in R. But the challenge is that they make checks, and when you don't comply, when part of your code doesn't comply with the rules of CRAN, then you are in the threat is that you might get removed from CRAN. So it's always a big panic when that happens. And I guess that the point here is that maintaining the package in a workable state, of course, we don't get any money for that. So we need partners, and we were lucky to have Quebec's Ministry of Wildlife, Forests and Park that support JR at this stage with other research projects as well. So some users are keen enough to see developments of the package so that we develop the package for their needs, but they are happy for the package to be useful to the entire community. And in terms of sharing, that the key is CRAN. So on CRAN, it's not very obvious on this graph because I've made the axis very small, but this is 2016 and this is July 2021, and the monthly downloads, so those are not cumulative downloads, they are monthly downloads, they're increasing steadily. So we have roughly, we're at about 3,000 downloads per month, which shows that the community is getting larger and larger. And we have this 150-page comprehensive user manual that Dave helps us maintain as well. So we've built a little community that allows us to share this package, which is being used more and more. So there's about 5 minutes left, and I want to conclude and provide a take-home message for that. You know, I guess that for this package, I want to talk a little bit more about the perspective of the supervisor. You know, the Lidar package, as I said at the beginning, my specialty is forest management and wood products. And the Lidar package has in some ways outgrown my research program. But this is a little bit weird, but this is actually a good thing. So I want to show that we've benefited a lot from that. It's a long-lasting contribution that, as I said, originated from a PhD project. And the key to this success were, among many others, first, the PhD candidate. JR is a special person with strong programming skills and a real desire to make his work shared with the community. That's not given to everyone to have this mixture of qualities. But also, I meant as a supervisor, it meant that I had to accept a different path. You know, all the time that JR has spent developing his package, he was not spending writing papers. And of course, with someone as productive as him, it was not much of an issue because I could understand the benefits. But I guess that it was not only accepting, but also encouraging him to follow this path in seeing that there was probably more that we could provide to the community with that, but also obtain ourselves. We needed strong support for partners. That was the AWARE project led by my colleague in UBC, Nicholas Coops, and the Quebec government. And also the team of enthusiastic users, contributors, some of which are listening to this talk right now. So, you know, I'm not saying that, I think we were quite lucky to have this sort of combination of assets to be able to develop the package. But the point here is that even if JR, it could be seen as something that's very generous, that he's been developing this for the community, and it is, but we have both benefited a lot from this work in many ways. You know, and what are the benefits? You know, the reputation, collaboration, citations. And look at, I mean, for the citations, look at, this is the Lidar package. That's the paper. It was published in 2020. My other work, I put a lot of effort on my other work as well. It's been cited once or twice. Of course, it's been published only last year. So the LIDAR paper was published at the end of 2020. I think it was November, December. And already in less than a year, it's already been cited 64 times. So of course, then LIDAR becomes a part of my research program. The principle, of course, in all this is that we should stand on, of packaging your work, is that we should stand on the shoulders of giants. That's the basic principle in advancing scientific knowledge. But for this basic principle to apply, giants must have shoulders, And in the development of the LIDAR package, GAR attempted to include as many algorithms as possible from the literature. And very often, it was unfortunately impossible to use or reproduce the algorithm for the information that was provided in scientific papers. And we are talking here about someone who has the capacity to interpret what's being written as best, a very unusual capacity to interpret what's being done. And even so, a lot of the work that we hoped would have been reproducible was not, despite being published in scientific papers. So I guess that's the key take-home message for grad students is not to develop another package like this that will be used by downloaded and maintained on CRAN, but it's about the shoulders. All grad students should at least think and consider packaging their routines. This means making sure that first, the most boring tasks in your analysis are automated. I think that's pretty much a given. Most graduate students I know will automate their task using coding. But also ensuring that the workflow is reproducible and that it's accessible, at least within the lab and preferably beyond. And that, I guess, the point also is to not underestimate the potential value of your code and routines for the community, because ultimately, if you make that effort, there's a good chance that you will benefit from that. On that, I will thank you for your attention. I will stop the screen share and I'm willing to take questions.
Great. If anyone in the audience has any questions, please feel free to either go ahead and put something in the chat, or if you'd like to either turn your screen on or unmute, we can, if there's not a ton of questions, you can go ahead and ask them. If not, we'll go ahead and call on people if there's a couple people that want to speak. Well, just in the interest of if people are writing some messages in the chat or something, I've got one I can throw your way if that's all right.
Yes.
I'm curious, have you, in any of your other work, been able to apply any of those tools developed in the package that you spoke of within the forest products and management realm?
Yes. So yes, so we've done a lot of work that's been commissioned by the Quebec Ministry. They've asked us, they have mainly worked on what they've asked us to work on is they've mainly used JR's ability to develop algorithms. So they've asked us to automate the detection of lakes, the detection of roads, which is a big issue in forest management, even the detection of power lines in LIDAR point clouds. But at the moment, what we're doing is that we're starting to use LIDAR data. And you're right. I mean, this is the way to link it to my research program is to use what we can learn from the structure of the point cloud and link it to what we've measured, not only in terms of biometrics, but also in terms of wood properties. And there are a few good examples of that in the literature. We haven't published anything yet on that, but I've got new grad students working on that right now.
Great, thank you. You've got a couple comments in the chat there, mostly expressing appreciation, but want to make sure you saw those.
Yes, so well, thank you, Connor. That was the I tried to make an effort, and I'm glad it was appreciated. Also, Pete saying thank you for. Yes, so yes, the NAU collaboration between Quebec and NAU, that's a great collaboration. In fact, if I want to say a few words on this, what I find, well, of course, it's for me, it's mainly based on Dave, who was in my team before, but what I find interesting there's an interesting parallel because of all the ecological restoration that of the Ponderosa pine forest and all the thinnings that need to be done in those forests. What seems to be the key issue there is, from my understanding of it, is that these thinnings need to happen, and there's a lot of volume in these thinning. And for these thinnings to happen, the key would be to be able to add value to low-grade timber, right? And in Quebec, we have very small trees as well, and we have a similar challenge. So very different environments, but a very similar challenge.
Well, perfect. On kind of the back of those comments, do you have any suggestions for grad students on how they could package their work outside of software like R?
Yeah, well, outside of software like R. So of course, I would say that any programming language would be good. The two main ones that are being used, I think, in our field is R and Python. And I think both have advantages. That I think what's great about R is the size of the community, the help that you can get. And also, I guess it's the fact that you can run lines of codes without having to compile. I think those are very important advantages. That's why I didn't talk about R much in terms of the advice that I wanted to give to grad students, because for me, the idea is more to automate the tasks. And so, whether you're using, I don't know if the question is, using different languages, like, I don't know if you can program in C++, then great. If you can use MATLAB or whatever, but what I would suggest in terms of choosing tools is to try always to consider what's the size of the community, how easy is it to use, and how well adapted it is to my my problem. And so I would recommend grad students not using Excel, for example.
Great. Any other questions from anyone else in the audience? Well, we'll go ahead and, I'm sorry, wait.
I was just going to say, it's been a year and a half of those awkward silences of any other questions, and then you see nothing happen, but I'm used to it. There's no problem.
Well, I'd like to go ahead and invite everyone to join us in the discussion section. Also, I know that Dr. Achim had brought up several papers in his work. If anyone would like access to those, I'm sure that you could email him, or I have access to them as well. If you see me around the building, please let me know. But again, thank you guys all for coming, and I hope that we can all imagine that we're clapping. And thank you for coming.
Thank you. Thank you for taking the time. Very much appreciated. And I see a lot of names that I've met before. Even some people I've met briefly a few years ago. I look very much forward to traveling back to northern Arizona, and I think the terrestrial border is going to open very soon between our countries. So it'd be great to come and visit again.
Sounds great. Well, I will see you over in the discussion section. You have the link for that and everything, correct?